Hello everyone, today we'll be creating a MATLAB function to perform linear convolution of input discrete time sequences. So here we have been given 6 discrete time systems and we have 4 input signals. So we'll be performing convolution of the 6 inputs of 6 systems and the 4 input signals that we have. So here I've created a MATLAB function to do the convolution. So first we will be defining the impulse responses of the system that are given to us. Impulse responses, the output of this system when the given input is delta function. So here we have defined 6 systems: h1 1 by 3, 1 by 3, 1 by 3 for 3 values we get. h2 when m is equal to 25 will be equal to 25 delta impulses. h2 when m is 50, h2 100, and system h3 is 1 minus 1, and h4 1 by 2 0 minus 1 by 2. This we have obtained after substituting delta n into the input system that are given to us. So let us first see how are the input system. So yes, these are the six impulse responses that we have. So we'll be doing the convolution with the 6 impulse responses. Now next, let us load the 4 input signals that are given to us. We have been given 4 input signals. One is baseline PPG, the other is the clean PPG signal. Next is the PPG AWGN for 10 seconds with the frequency 25 decibel voice, and next is PPG AWGN with 20 decibel voice. So we have these 4 signals. We have loaded them into MATLAB with the help of the load function which is available in MATLAB Plus, and MATLAB automatically assigns variable to this. And so these are the 4 input signals that we have: XB2 first signal, X2, X3, and X4. These are the 4 signals that we have, and we'll be doing the convolution of these 4 input signals with the 6 impulse responses that we defined earlier. Now to do convolution, we have defined the convolution function over here. So this is the convolution function. It takes in the signal and the impulse response as the input. Now as we know that the total number of non-zero elements in a convolution is equal to the length of the input signal plus the length of the impulse response minus 1. So similarly here we have defined A as length of x, B as length of the impulse response, and we have run a loop from we have run a loop which goes from 1 to A plus B minus 1, and similarly inside this loop we correspondingly we have run another loop which goes from A to I to A, and as per the definition of convolution we have defined output of I is y plus x of j plus into h of I minus j plus 1, as is with the definition of convolution. As in discrete time system, convolution is equal to summation x of n h of n minus k, where k belongs to minus infinity. So here we have defined the same. We have multiplied and done the summation and done the sum of each and every term to obtain the summation. So coming back to the signal, so firstly we'll do the convolution for the signal xb2, the first signal with the 6 impulse responses that we have. So for this we'll pass in the input signal xb2 and h of 1, the impulse response of first impulse response, as to the convolution function and obtain the corresponding output. So here we can see that for the signal xb2 we have 6 outputs corresponding to 6 input systems impulse responses: xb2 y1 with the first impulse response, xb2 y2 with second impulse response with m equal to 25, then with m equal to 50, m equal to 100, then with the third system, and then with the fourth system. So these are the corresponding output that we have. Similarly, we have defined the same function for x3, x4, and x of 2. As in case of x of 2, we'll pass in the input as x of 2 and h of 1. Similarly, x2, h2, for 25, for 50, 100, then x2, h3, and x2, h5. And this is the output that we obtain for the signal x2, performing the same calculation as we did for xb2, passing in the input variables to the convolution function and getting the output. Similarly, we have obtained the output for x3 input signal, and this is the output that we get for different input systems. And similarly we have plotted the output for the x4 system: x4 y1, x4 y2, x4 y3, x4 y4, as 6 inputs as we can see over here. Now next thing which we observe is that in the input signals which we have xb2, x2, x3, and x4, we observe that in the signal xb2 we observe a trend in the signal. That is, it is not continuous, it is not a clean signal, it does not go in a straight line, rather we observe a trend. This trend is known as the baseline wander. As we can observe, x2, x3, and x4 are straight signals, they do not are clean signals, do not have any baseline wander, but the signal xb2 has a baseline wander. So we'll try to remove this baseline wander. So to remove this baseline wander, what we do is we defined an impulse response, an impulse of 100 response, an impulse response of 100 value from 0 to 100 of delta function. So this is repellent 1 by 100 to 100 we have defined here, and we'll do the convolution of the signal xb2 with this impulse response h underscore m to obtain the baseline wander. The result which we obtain from the convolution of xb2 and h underscore m will give us the baseline wander y underscore m. And to get the clean input signal, that is to remove the baseline wonder, we will subtract this y underscore m from the input signal xb2 that we have. So for this we have run a loop over here to subtract the corresponding elements from of y underscore m from xb2. And after subtracting this, what we'll observe will be a clean BPG signal after removing the baseline wonder. And as we can observe in this figure, this is the input signal, this is the baseline wonder which we obtain from plotting the obtained by the conversion of xb2 with the impulse response h underscore m which we have defined for 100 values. And this is the baseline remove signal that we observe. This is the clean PPG signal. Now the next thing that we have in the system is to determine the how the system is to determine the filtered signal, the function of each of the system. We have to write the observation on the filtered signal, the input signal. We have to describe the function of each of the system. We have 4 systems over here, so we have to describe the function of each of the system. So as we can observe that in the input signal xb2 has a shift which is known as the baseline wonder. And so if we observe the outputs of the signal xb2, we can see that for system 3 and 4, the output we get is distorted and discomfort. If we observe the output of xb2, we observe that for x3, for system 3 and 4, y3 and y4, we obtain the output as little distorted and this compact. So therefore the system 3 and 4 are high pass filters, and correspondingly system 1 and 2 are low pass filters, because for system 3 and 4, for the input signal we get a distorted and a compact graph as we saw right now. Therefore the PPG is a low frequency signal, and correspondingly signal system 3 and 4 are high pass filters and system 1 and 2 are low pass filters. The next question which we have is to write all the properties of the above mentioned discrete systems. Now as already mentioned, all the above discrete systems are linear time invariant signals. All the systems are linear time invariant LTI systems. For system 1, we observe that it is a memory system because it depends on its past values, and is a causal system because it depends on the past and the present inputs, and is a bounded system because when our input is bounded, then the output that we get is also bounded. So as for bounded input we get bounded output, therefore the system is a bounded system. Similarly we can see that system 2, 3, 4, all the systems are a memory system because they depend on past values. They are causal because they depend on present inputs, and all of them are bounded because if we bound the input, the output that we get is bounded output. Therefore we have defined all the properties of the systems.